I'm going to be talking today about gravitational fields and like rocket ships, and as they sort of, go around planets and stuff like that. So, is there a gravitational field outside sort of the atmosphere?
Yes.
Absolutely. And do you remember me drawing that gravitational field kind of like this, right? And do you remember the rule about where the gravitational field is strongest? In relationship to the gravitational field lines. What's the rule? It's like, where is it stronger? Where the lines are closer together, right? So down here, the lines are close together, and up here, they're further apart, right? So, no, well, you can if you want.
Are we drawing something?
You can if you want. There's actually, it's on the left-hand side there. It's all there, already there. I'm going to. I'm just kind of giving you sort of an intro here. Okay, so the whole idea of this field concept is, remember me doing that demonstration where I tried to move the tennis ball using the force, and I was unable to do so? I've not passed my Jedi Master training. You have to be in contact with something, whether push it or like a rope or a string or a chain to pull it, right? But the spacecraft is not in contact with the Earth. So how can there be a force? So scientists came up with this idea of a force field. Force field name. And would you say that this rocket ship is in contact with the force field? Absolutely. Now, just because there's no line, like right there, you say, okay, well, yeah, it's touching the blue line, touching the force field. But what about right there? Still there. The lines themselves are a scientific model. Remember that idea from earlier on?
It's not like big neon lights that point in all the planets that show where it is.
Say that again?
So there's not like big neon
No.
lights in space that point show the gravity.
Pluto, this way. 8,000 miles. Do these, if you could put on special gravitational field glasses, would you see the blue lines? No. Do they actually exist? Not physically. It's kind of just a model. It's a way of explaining it. And so this ship is still in contact with the field. Okay. Let's get right into the actual reading here. So that's what they're going to be getting at. I sort of gave you the quick version to get you started. Gravitational fields. The Earth pulls on the moon. We regard this as action at a distance, and I am going to highlight that. I am going to highlight that, if I can. First page, first sentence. Action at a distance. Why do we say action at a distance? Because there's nothing, what? No contact. There's no contact. Because the Earth and Moon interact with each other even though they are not in contact. Or we can look at this in a different way. We can regard the Moon as interacting with the gravitational field of the Earth. The properties of the space surrounding a mass can be considered to be altered in such a way that another mass introduced to this region will experience a force. This alteration of space is the gravitational field. Sometimes I wonder if it would be more entertaining if I did this lecture using a Stephen Hawking voice.
Do it.
Probably not. It'd be funny for about 10 seconds, then it would just get stupid.
Like the shoes you put on and you bounce around.
I don't know, man.
You never put on moon boots before?
I don't know. Yeah?
You've never worn moon boots.
I've moonwalked.
You've never worn moon
What do you mean?
balls.
Oh.
You guys don't know what a moonwalk
Yeah, I
is?
do.
I can't.
Come on, Mr.
Oh, yeah, you can't? Come on. You guys never moonwalked? I'd have to, let me practice first. I don't want to look foolish. Yeah. Why did I say that?
Disappointed.
Why did I say that, Sam?
Because you really want to move on.
Oh yeah, I really do. Yeah. I woke up this morning and said to myself, it would make my day really looking stupid in a bunch of teenagers. Oh, hang on, I do that every day. Thanks, Kia. Like we care, she says. I'll have to remember how to do that. How does that go again? Something like that, yeah. I'll have to think about it. Did I get it? I remember practicing when I was your age. Jeez.
Practicing on a moonwalk?
Yeah, well, it was cool, man. It was like
Wait, hey, what
Like my
music
back?
video did the moonwalk actually come out in?
Okay, so common to think of distant rockets and space probes interacting with gravitational fields rather than with the mass of the Earth and other planets or stars that are the sources of these fields. The field concept plays an in-between role in our thinking about the forces between different masses. So the field concept is simply a model. It's a way of explaining how these forces work, because we really can't wrap our puny human brains around the idea that you can experience a force without contact. And if you stop and you think about it for just a second, it's crazy talk. The Earth pulls on the moon even though there's nothing to, like, is there the force out there, Jedi Masters?
Yeah.
I don't know. Probably not, but if big inanimate objects like planets can do it, how come smart people like us can't?
Not enough.
Things like magnets.
Things like and magnets create magnetic fields.
Because Isaac Newton wasn't smart
Well,
enough to have children.
And technically we do have a gravitational field, it's just not very strong. Here it is here too. A gravitational field is an example of a force field for something in the space experiences a force due to the field. Another force field you may be familiar with is the magnetic field. You've probably seen iron filings lined up in patterns around a magnet. The pattern of filing shows the strength and the direction of the magnetic field at different points in the space around the magnet. Hey, when you hear the words strength and direction, what breakfast cereal pops into mind? Vector. Are you saying that magnetic fields are vector quantities, Mr. Bennett?
What is vector?
If magnetic fields are vector quantities, what about gravitational fields? Yeah, they're a vector, which means they have a strength and a direction. What direction is the Earth's gravitational field? Down. The pattern of the Earth's gravitational field can be represented by field lines. Like the iron filings around a magnet, the field lines are closer together where the gravitational field is stronger. Important concept. At each point on a field line, the direction of the field at that point is along the line. Arrows show the field direction. A particle, astronaut, spaceship, or any mass in the vicinity of the Earth will be accelerated in the direction of the field line at that location. The strength of the Earth's gravitational field, like the strength of its force on objects, follows the inverse square law. And the inverse square law says what? Does anyone know? I have a little star on mine here. Do you? Do you have something at the bottom of your page?
No, I don't.
No?
Obviously, it's reversed.
Inverse square law means that if you're twice as far, do you have room to drop this in? Put the little star. 2 times as far means what, Nate?
What?
2 times as far means how much times as strong?
2 times as strong.
Half as strong.
That's
Not half. Inverse square. 1/4. Where did the 4 come from? 2 squared. 3 times as far?
Oh.
1/9. 4 times? 1/16. We're simply squaring it. That's the inverse square law. Same thing is true for sound. Same thing is true for light. Okay? If John over there holds up a light bulb, right? And the distance to Chandler is, say, I don't know, what, about maybe 4 meters? Okay, so he's going to see a certain brightness, and I'm over here about 8 meters away. I'm twice as far, so I'm going to see the light 1/4 as bright.
The second one starts with 1.
No, 4 squared. 1/4 squared. Not 4 times 2, 4 squared. Lucas.
So if you're like jumped out of like a space craft,
Yeah.
and you're like just outside like of the Earth's gravitational pull, it will eventually pull you back to Earth.
Okay. How far would you have to be outside the Earth's gravitational field strength? Oh, way farther than the moon.
Wait, like how many
out of our
miles away is the
atmosphere.
moon?
Well, it's always going to exist just because weaker.
Exactly, and you're more than likely to be in someone else's even stronger field. right? Like if you're, 100 meters above the surface of Mars, you're still in Earth's gravitational field, you're just in a much stronger field, not being Mars.
Okay, so like if you're like halfway between Earth and the Moon, you're gonna get pulled towards Earth.
So each planet
Yes,
has
but because the Earth's bigger, it's stronger.
The Moon is in Earth's gravitational.
Correct.
But does the Moon have its own? It has its own.
Yeah, it's 1/6. Remember the pictures of the astronaut dropping the stuff? Right? Remember that? There's gravity there. Yeah.
Because it's why is that number?
Smaller?
No. Where do you get 1/6 from?
Actually, the moon is 1/6 the volume, basically. Mass.
So 6 moons. I thought like that's the sun, like 100.
Yes, that's the sun.
Yeah.
Yeah.
Gotcha.
So the moon is about 1/6 of the size of the Earth. Yeah.
Gotcha.
Okay, good. So here's the fun part. The gravitational field of the Earth exists inside the Earth as well as outside. If you were to dig a hole a foot down, would you float? No. Gravity is clearly there. If you go 10 feet down, 100 feet down, 1,000 feet down, there's still gravity.
And water.
To investigate the field beneath the surface, imagine a hole drilled completely through the Earth, say from the North Pole to the South Pole, because that's the way people like to imagine it. Forget about impracticalities such as lava, high temperatures, it being really cold at the start, all that stuff. Consider the kind of motion you would undergo if you fell into such a hole. Now, we've all seen cartoons where this happens, right? Bugs Bunny or whatever. Yes, Nate?
We watched the movie The Core.
You know what we could do is watch it and pick out all the scientific inaccuracies in it.
Let's do it.
Yeah.
Something like that.
We're going to talk about that right away. We're going to talk about that. Okay, so if you started at the North Pole end, up here, you'd fall, Nate, you'd fall, you would gain speed all the way down to the center. Why would you gain speed? You're falling, there's acceleration. You would overshoot center. How come? Because you're already moving. You'd overshoot, you'd lose speed, you'd slow down all the way up to the South Pole.
How many miles is it thick?
I'm gonna answer all your questions. I really am. Okay?
Yeah, wouldn't it just fall into?
You would fall all the way down, you'd overshoot center, okay? You'd lose speed all the way up to the South Pole, and you'd gain speed moving towards the center, lose speed moving away from center. Without air drag, the one-way trip would take nearly 45 minutes. You would free fall 45 minutes to the other side.
Going back and forth.
Exactly. If you went all the way, if you failed to grab the edge, if there was a guy, kangaroo out for a walk, and Nate jumped in a hole, and they were standing there right at the exact point, and their hole was there, what would they see? They were standing there, and Nate came flying through the hole. What would they see?
A flash before their eyes and they get crushed.
No, they're standing right beside the hole,
Already standing there.
waiting for Nate, just waiting, standing there,
45 minutes.
listening for a minute.
Would you see him fly up and then back down?
And not only that, he would be
On fire.
true enough. Actually, he wouldn't be going fast. He would rise, right? If he's like this tall, right? He would come up exactly that height, except he'd be upside down. Wouldn't he come up like, you'd be standing there, and all of a sudden, boom, there you Nate, upside down, feet in the air,
Obviously.
and then what would happen right away? Right back down.
If nothing
Gone.
happens.
If you didn't grab hold of him.
So it would slow
So that's
down.
if you could go right
and
through the
then
Earth's
just go.
center.
Yeah.
Yeah.
And it would take 45 minutes.
Kind of like the rabbit hole.
Might know.
Exactly. Okay?
Maybe it's
Now, you're all wondering, okay, well, let's go send Nate on that trip. Right? So, let's zoom into Dauphin here. It doesn't really matter where in Dauphin, but that's where he would come out, right there.
Where?
That's bullshit.
Says the nearest country is.
Nearest country, 0 results. Nate would come out right about, well, he'd have a long swim.
Wouldn't they just win the whole scope of water?
Little island right there, Mr. Bennett.
You are literally the middle of the Indian Ocean, right there. There's a little island right there, but you are as far away from Australia
Those tribal people say.
as we are from California.
He was in Mexico now, where would he be?
He'd have to pack a lunch. What is that little island right there?
Mr. Barrett, I eat a lot of lunches.
I'm sure you do.
Stuff.
The French Southern and Antarctic lands.
You have to go to California.
Everyone goes there, big tourist trap. Right? Where would you have to dig? You'd have to dig somewhere south of Medicine Hat to end up there, and you wouldn't want to miss.
Why is it like that?
So yeah, that whole China thing. If you were actually to dig a hole, where would you have to dig to end up in China?
Go to China to see.
Exactly.
Cool. I don't think there's any bigger
Or like-
island. Yeah, good job. I don't like the sarcastic,
You'd have, yeah, somewhere in Argentina you'd come out around China, and Mitch can confirm, that's why I got the globe out, right? China, opposite Argentina, right? There you go. Walt Disney was fooling you all those years with Bugs Bunny.
I don't think Bugs Bunny's going from Argentina.
There is a Bugs Bunny one where I remember he comes out and he's wearing like the stereotypical racist Chinese hat,
Yeah.
with the Chinese stereotypical mustache, banging on some gong or something or other. I remember that cartoon. Repeat this trip with an accelerometer of some kind. Now, what the heck is an accelerometer? Measures
I
acceleration.
know that because of the clusters.
Do you? Your acceleration at the beginning of the fall is g, 9.8, but you'd find it progressively less as you continue toward the center of the Earth. How come as you fall, like so, your acceleration becomes less? Why?
Aren't the T ends with an L?
Remember, gravity is based on the mass of the planet, right? So as you fall, like if you're sitting right here, not sitting, you're right there, how much planet is below you?
A lot.
But there's still some planet above you. And are you gravitationally attracted to the planet above you?
Yeah.
Yes, you are. So there's a pull down, but there's also a pull up. But when you're standing on the surface, well, the entire planet is below you. So technically, gravity reduces as you go towards the center of the Earth. It's about, divided by 2, about a quarter of the way down, like so. So why? Because as you're being pulled downward toward the Earth's center, you're also being pulled upward by the part of the Earth that is above you. In fact, when you get to the center of the Earth, the pull down is balanced by the pull up. What's the net force?
0.
0. How come you don't float?
I'm fat.
Because you're already
Floating.
moving.
If you were able to stop the motion, you just float in the middle of the
Yes. If you were able to crawl a ladder all the way down to the center of the Earth, and then just sort of jumped off, what would you do?
Stay there.
You'd float. But if you misjudged and you didn't get off at the exact center, what would happen?
And go up or down.
You'd fall up and down like this, and you'd never get to either edge.
Grab back on.
You'd have to grab back on the ladder.
Yeah, you thought you were pretty smart when you made that joke.
That wasn't a joke. I'm just naturally funny. You are pulled. I'm glad you got it though. You're paying attention. That's good. In fact, when you get to the center of the Earth, the pull down is balanced by the pull up. You are pulled in every direction equally, so the net force on you is 0. There is no acceleration
Wait, you said every direction equally?
as you whiz with maximum speed past the center of the Earth. The gravitational field of the Earth at its center is 0. Now, because there is air resistance when Nate jumps in the hole, is he going to pop up upside down in front of the Australian's backyard? No. Because air resistance means that he will not accelerate enough to get there. He will, in fact, go fall all the way down, and eventually he'll run out of speed, about there. And then he'll fall back the other way to about there, and then eventually, after probably, a few days, he'll bounce back and forth and end up just floating there at the center. It would be cool.
I think if you,
So you get,
We should go on a field trip.
And do one hell of
Dig
a
a hole and
you
see.
just have to drop clean water down the hole.
One hell of a death. That's what it was doing.
Yeah. Well, if he doesn't, let's get it in, let's get it on the other way.
Yeah, that's true. If he misses it, just be
Yeah,
Let's
I'm
get
doing
it on
that.
there.
The strength of the gravitational field at any point is measured by the force on a unit mass placed there. If a force F is exerted on a mass m, the field strength is F over m and its units are newtons per kilogram. So gravitational strength of the Earth, 9.8 newtons per kilogram. And when I jump on the nerd scale, what else are you going to call bathroom scale measured in newtons?
Why did you buy one like that? Why didn't you just get one in kilograms and convert it?
It was given to me.
Why didn't you just convert it into newtons?
It's already in the movies.
Never mind, we just forget to ask that question.
I got a phone call. Hey, we got a bathroom scale at our school, but it's got something weird on it. It's like, it says it's in newtons. I'm like, get it over here. That's awesome. Elementary school had this. Why? I have no idea. What was I saying? Oh, yeah. I'm bad for that, aren't I? 9.8 newtons per kilogram. So every kilogram of my mass is registered with 9.8 newtons down here, right?
So should you subtract 9.8 when you...
How much is it, Savannah?
No, 800.
So should you subtract negative...
How do you find my mass? 800 divide by 9.8.
81.6 kilograms.
81 point what?
81.6.
kilograms?
82 kilograms. If you want it in pounds, you're going to have to multiply by 2.2.
Pounds.
Oh, jeez. I better moonwalk my way home and try to drop a few pounds.
180 pounds, Mr. Bennett.
Oh,
We're going to keep track of your weight till the end of the school year.
it's always 800. Thanks. Interestingly enough, you would actually gain this is sort of a legal aside kind of thing here. You would actually gain acceleration during the first 2 kilometers beneath the Earth's surface because the density of surface material is much less than the condensed center. The mass of Earth above you exerts a small backward pull compared to the disproportionately greater pull of the denser core material. This means you'd weigh slightly more for the first few kilometers because you're technically closer to a greater density of mass. Don't worry about that. And then this link here takes me to that same one that I just showed you. Just a different one.
Back going through the Earth.
This was going to be the highlight of my day.
Well, I apologize. All right, all I can do is ask you manually. I apologize.
It was going to be...
If you stepped into a hole through the center of the Earth and made no attempt to grab the edges at either end, what kind of motion would you experience? Would you fall all the way through at a constant speed and stop when you reach the other side?
No.
Would you fall all the way through, speeding up the entire time and stop when you reach the other side?
Nope.
Would you oscillate back and forth with a changing speed, which is known as simple harmonic motion? Oscillate means from like,
C.
yeah, go back and forth. Or would you oscillate back and forth with a constant speed?
C.
C.
I am a C.
You would oscillate back and forth in what is called simple harmonic motion. Each round trip would take nearly 90 minutes.
Why does it say 45?
It was 45 one way.
Oh.
Interestingly enough, we see in the next chapter that an Earth satellite in close orbit. Okay, what are you guys doing?
Yeah.
Just listen. If you're in orbit around the Earth, it also takes 90 minutes. So it doesn't matter whether you go like that or like that. How come? Because gravity's the same.
So if we
Doesn't matter. Would you give me that?
So if we went from the top of the Earth and fell right to the bottom,
Yeah, but all I hear is this. It's empty. What do you need it for?
What if you strapped it? What if you're strapped in there with rocket roller skates on?
It takes 90 minutes to go all the way around.
I mean the Earth,
Mr. Bennett,
the whole Earth.
what happens if you strap a pair of rocket roller skates on and jump down the hole?
I wonder what this does here.
Somebody's gonna get attacked.
You know.
You know, I once I was refereeing hockey.
Can I pause
The
it?
guy in the corner was literally screwing around, and so I gave him a penalty. 2 minutes for screwing around. That's what I'd like to do right now.
Give him a do
I went to the timekeeper's box and I said, 2 minutes for screwing around. He says, how am I going to write that down? I said, I don't care.
it. 2 minutes out of class.
When we played service, I got like over 100 yards of penalties for unnecessary roughness for just knocking crap.
Yeah, I know. I don't want to show you this.
I'm really surprised they never kicked me out. It was bad. It was bad. I was just getting kicked so late, like it was bad.
Don't, Nate. It's funny for a while, but you've gone too far. Do you need another sheet of paper yet, Josh? Getting there? Halfway to the center of Earth, would you weigh more or weigh less? Remember, your weight is actually The measure of the Earth's gravitational pull on you, you would weigh less.
Why? Just not tell me.
I'm going to tell you. You would weigh less because the part of the Earth's mass that pulls you down is counteracted by the mass above you that pulls you up. If the Earth were of uniform density, it's not. Halfway to the center, your weight would be exactly half your surface weight. But since the Earth's core is so dense, about 7 times the density of surface rock, your weight would be somewhat more than half surface weight. Exactly how much depends on the Earth's density. Varies with depths. Stuff they really don't know yet. They don't know what is really at the core down there. Maybe there's some little mouse on a treadmill. Who knows, right?
Being weightless is like something that you can attain by being massless.
You cannot, exactly. Okay. Well, let's revisit the idea of weight and weightlessness. The force of gravity, like any force, causes accelerations. Objects under the influence of gravity accelerate toward each other. We are almost always in contact with the Earth. For this reason, we think of gravity primarily as something that presses us against the Earth rather than something that accelerates us. The pressing against the Earth is the sensation we interpret as weight.
Sensation. What's a sensation?
Like the feeling.
Oh.
Stand on a vacuum scale that is supported on a stationary floor. The gravitational force between you and the Earth pulls you against the supporting floor and scale. By Newton's third law, the floor and spring in turn push upward on you. Located in between you and the supporting floor are springs inside the vacuum scale. The springs are compressed by this pair of forces. The weight reading on the scale is linked to the amount of compression on the springs. Just like the weight things, the spring weight things there, those big circle scales, right? When you pull on the spring, it makes the needle turn, right? Opposite.
What if you have a digital scale?
It's still kind of the same idea. I guess it'd be like some sort of sensor that would probably electronic thing. One of the ways that you can create electricity, you might have learned in grade 9, is a piezoelectric crystal, like in a microphone. And when the more stress that's on it, the greater the electric current, so that's probably something like that, a digital scale. Man, you're smart, Bennett. All right. If you repeat this weighing procedure in a moving elevator, you would find your weight reading would vary not during steady motion, but during accelerated motion. If the elevator accelerates upward, the bathroom scale and the floor push harder against your feet, and the springs inside the scale are compressed even more. The scale shows an increase in your weight. We've talked about this already. There is a picture that might help you understand it more. Look at the picture. Normal weight, standing there with really bad haircut. Greater weight, how come? Accelerating upwards, right? You can see the little clouds of dust here. That's the universal cartoon symbol for acceleration. Less weight because they're accelerating down. Why no weight? Free falling.
Mr. Bennett, I'm sure there's
Yeah.
more safety measures in place. There's one little string holding an elevator.
Oh no, that's how elevators work. Just one little string.
Just one. It's like fishing line.
Yeah.
I got it weird.
If you define weight as gravitational force acting on an object, then you still have weight whether or not you are freely falling. Astronauts in Earth orbit who float freely inside their capsules are still being pulled by gravity and therefore have weight. But you in the falling elevator and the astronauts in the falling satellites don't feel the usual effects of weight. You feel weightless. That is, your insides are no longer supported by your legs and pelvic region. Your organs respond as though gravity were absent. You are in a state of apparent weightlessness.
So how does that affect your insides?
Well, your astronauts that go up there, that's why they have to exercise up there, right? Because just like, has anyone ever had a cast like on a leg, broken leg or something like that? And your muscles get really weak? Same idea, right? When they're up there, because like we are constantly fighting against gravity, so our muscles are constantly exercising. When you're floating around up in space for 6 months, your muscles literally atrophy, and when they come back to Earth, they can't stand. They have to basically go through rehab because they become so weak. Yeah, because you got no strength in your legs. That's why they exercise and they try to do as much as they can there to produce that. It's one of the problems with colonizing planets that are farther away. Is like it's one thing to go up into the space station for say 3 months, right? But to go to like Mars or whatever, and the distance it is that the humans, by the time they get there, they're not going to be able to walk around because they got no strength. It's one of the things they got to solve. Steroids.
Yeah. Totally.
Would that affect what happened in your leg? Ooh. I think the muscles inside your body, like the biological, like that, doesn't it not actually push the food down?
Yeah.
Some of this gravity cut? I know that's a big question, I don't know.
That's why if you eat something and
It's
you're
not,
standing on your
are you
head,
bench wrestling?
I don't know who was saying that. But if you're like on your head, you like eat something, your like muscles in your stomach.
Yeah, I think you can still, yeah, I think so, yeah.
I don't know how it's gonna work if you're like drinking water or something.
Yeah.
I don't
I don't know.
Really turn down the on space station.
No, they don't have artificial
Sitting
gravity.
around bench pressing. Really.
Yeah, well, yeah, they can lift like nothing because there's no gravity.
So what's the point of working out?
Well, I mean, like they do, like they ride bikes and stuff like that to try to exercise as much as they can. Okay, almost done, and then I'll be quiet. To be truly weightless, you would have to be far out in the space, well away from the Earth and other attracting stars and planets where gravitational force is negligible. You have to be so far away from stars and black holes and everything. In this truly weightless condition, you would drift in a straight line path rather than in a curved path of an orbit. In a more practical sense, we define the weight of an object as the force it exerts against the supporting floor or weighing scales. According to this definition, you are as heavy as you feel. The condition of weightlessness, then, is not the absence of gravity, but the absence of a support force. Ooh, that's a good one. Right? Weightlessness is not the absence of gravity, but the absence of a support or normal force. That queasy feeling you get when you're in a car that seems to leave the road momentarily when it goes over a hump or a bump in the road, or worse, off a cliff, is not the absence of gravity, it is the absence of a support force. Astronauts in orbit are without a support force and are in a sustained state of weightlessness. This causes space sickness until they get used to it.